Welcome to the Intersecting Us podcast, where math and life intersect.
In this week's podcast, Brian and Dave discuss the power of imagination, from fixed math to growth mindset.
Well, hey, everybody. This is Brian and Dave at Intersecting Us, another podcast for you. I think as you either driving down the road or however you listen to this podcast, probably are thinking of something, maybe imagining things. Today, we're going to talk a little bit about imagination and how that works in our lives and how it makes a difference in the way we think and sometimes the way we live. So, Dave, I think you said you told me earlier you were imagining something from the past podcast that you kind of wanted to talk about. So why don't you go ahead and start us off with that, and then we'll get into it.
Sure. Well, thanks, Brian. Hello, everybody. Sometimes my imagination goes wild, and that means things that come out of my mouth that need to be clarified. And one of the things I was thinking about in a previous podcast is I was listening to it, and it's not necessarily wrong, but I was kind of like ruminating on it and realized, I think I've got a little different perspective on it than I first talked. And so I just kind of wanted to maybe highlight that real quick. And Brian, back in the previous podcast, we talked about the difference between pi and E. And one of the things about pi is that it shows up in the real world because it's connected to a circle. And because of that, it's been around a long time, that we found a long time. But then I talked about E, that really doesn't show up in the real world, but it does show up in the math abstract world, and that there's not like a physical representation of it. And I started thinking about that. And I think that really that is not completely accurate, because we also talked about the natural logarithm and what is the area under the curve of 1 over x. And if the listeners remember that podcast, you'll remember we talked about the area under that curve as you go from 1 to E was actually 1. And the point that I just kind of wanted to bring up today as we think about a previous podcast is that area is like a representation of what E is. And I had never really thought about that before. We think of pi as a ratio of the distance around a circle divided by the distance across. So we're just kind of think of it in terms of a circle when we think of pi. So it exists out there in the real world, but there's not like any representation of E. And I think that that's not completely accurate, because we've got that very simple representation there as an area under a curve. And, it's the hyperbolic curve, which is part of the conic sections. And so it's actually closer to pi than I had even thought about, because, pi is connected to a circle, which is also part of a conic section. So really both are connected to conic sections. One just happens to be the hyperbola, and one just happens to be a circle. It's just that E is less well known and requires a little bit more imagination to actually see it, but it still exists. So anyway, that was enlightening for me to see. And I was excited to see that. But then my first reaction was that, oh no, I think I misled people on our podcast. And that was kind of like a disheartening feeling. But then I started thinking more deeply about, that feeling. And I realized that is a bad way of approaching that, because I want to be approaching math like something that I'm always growing into and I'm learning from. And in the process, we're always going to say things and do things that may not be perfect or 100% accurate, but that's part of the growing process, is that we're going to maybe say something one day, and then the next day we're going to think like, I've got a better way of saying this. And I think if we start thinking about math in that we can't make those kind of, I'll call them mistakes, even though they're not mistakes, but they feel like a mistake, that keeps us from really growing in doing our math. And so, today we're going to talk about imagination And that really requires us to get out of our comfort zone and into a different world than we're comfortable with.
Well, I know when we look at math, it seems often just in the general population that if you're going to use imagination, that would be more, like artists or, authors, things like that. If a sculptor is going to make take a piece of rock and then chisel away. How do they say that? You chisel everything that isn't the sculpture,
Right.
But you're imagining something. You may have written some stuff down, but that type of mental acuity of imagination seems to go well in those types of fields, art, even in science, but certainly in math. It seems like that's just kind of a numbers game, as they say, and you just go through formulas and it's just rudimentary and you just, go through the steps and you don't really have to imagine anything. You just do it. It's boring, if some people think, And I think you've hit this already in the podcast, but as you said, there are, that's not is that the only way to look at math, and maybe not the best way to look at math. So talk a little bit more about what you mean by, how you use your imagination in doing math.
Yeah. I think that one of the things we think about in math is that it's got this right answer. So where does imagination come in? And before maybe I answer that, I've got a couple of quotes that I kind of wanted to tee things off a little bit. And one of them comes from David Hilbert. He's a famous mathematician, lived around the 1900s. And he was told that one of his students was going to drop mathematics to become a poet. And he's a college professor. And Hilbert's reply was good. He did not have enough imagination to become a mathematician. And like you said, with kind of like artists, we think that imagination is part of the artist world. Why is it that we need imagination to become a mathematician? Because when we first start off, what we are exposed to are a bunch of rules. But once we get over that thought, at the core, math is simply abstract ideas. There's nothing concrete. We're not limited by things that are in this world. We can imagine anything we want in math. Now, it doesn't necessarily mean it's true, but because it's abstract, we have much fewer limits than we would, let's say, if we're a physicist or a chemist or a biologist who are limited by what actually happens in the real world. So the boundaries for a mathematician are extremely wide. If you give me a problem, I can use algebra to solve it. I could use geometry to solve it. I could use calculus. I could use circles. I could use triangles. There's all kinds of options that I could choose to use. Now, maybe not all of those work, but I'm free to choose any of those options. And more often than not, if you get a solution using one method, there usually is many other methods to get to the answer. And that's kind of one of the beauties of math, is finding different ways of getting the answer.
We just have this huge range of options at our disposal to get the correct answer.
Yeah, and I think that's, as we talked a little bit before, the freedom part is the biggest part that I think most people in life, they look at math as being very concrete and you follow a set of rules, and everything else, you got to have freedom. But you're talking more about the fact that because math is not physical, I guess we could call it that, it's more abstract ideas, that you can actually have more freedom in math than you do in pretty much any other discipline.
That's right. And I work with that actually quite a bit in my day job at coaching actuaries, working with students and helping them to see that when they solve actuarial problems, what I encourage them to do is I encourage them to follow basic principles. And that means that they have a lot of freedom into how to follow those basic principles. So it's not a prescriptive approach, but there's an opportunity for them to use their imagination to apply those principles.
Yeah, and that starts to make sense. It's got kind of we do that in science, with the scientific method. You go down a path, but you got to kind of choose the path, and then sometimes you find out, oh, that path has a roadblock, and then just you back up and try another method. And math has that same type of concept, but it seems like it's even more free because you don't have the physical constraints that you would have in something like physics or biology or those types of disciplines that you'd use those methods with. But I did have to ask you, you talked about Hilbert, you had a quote from him. Is that the same guy that did the Hilbert's Hotel?
It is. Yeah, that is kind of a famous story that goes around in math circles. So a lot of people in the math circles have probably heard it, but there's a good chance probably a lot of our people who listen have not. Do you want to tell that story?
Yeah, it was a philosopher that I heard it from, but it's, if I remember right, it was if you have a infinite number of rooms in a hotel and they're all full. And so some guys wants a room. So what do I do? Well, it's infinite. So you just move everybody over one, and then the first one's open. Then they do things with odd and evens, and we don't have to get too deep into it. But it's a whole idea of how math with infinity works, because, as we talked in prior podcasts, the set of odd numbers is infinite. And so the set of even numbers is infinite. And the set of all numbers, just both of those together is also infinite. So in some ways they're equal, but in kind of an infinite way of looking at it, they're really not. And that's kind of how Hilbert kind of helps us with that. But probably a nice story for a different day. But I think it's interesting how these guys, you hear these names and I'm like, oh yeah, I've heard of him before. And it is a really neat way if our audience wants to look up Hilbert, his hotel, it is kind of a neat way of looking at how you try to explain to somebody how infinite items and infinite sets can interact with each other. It does not make sense in real life, really, because it just goes on forever. But I think the whole idea of Hilbert, and then you're talking about the way you use freedom in math, it's a way of looking at math that's more fun or rewarding or joyful or beautiful, all those different words we've been using. I think that's one of the things that you're trying to do, is to try to get people to look at it from a perspective that is different, certainly, but more full and more meaningful and actually more real, I think.
Mm-hmm. Yeah. One of the things I've recently ran across that I think highlights this idea that's pretty cool is the proof of the Pythagorean theorem. And of course, that's been proven for thousands of years now, when that proof first started. But I don't know, Brian, if you have any idea, you probably, if I was to ask how many proofs there are, my guess is you might think that there's more than one proof of the Pythagorean theorem. Would you agree with that?
Well, it seems like that'd be the way to go. I mean, because just using odds, the chances of only one is probably lower. But
right. And so I recently bought a book, and the book purpose is to go through the different proofs of the Pythagorean theorem. And I don't remember the exact number, but it was over 200. There's 200 different ways that we've come up with over the thousands of years of proving the exact same thing. So on one sense, there's no creativity because the Pythagorean theorem still holds. In other words, nobody has disproved it. But we have hundreds of stories that are different that get us to the exact same answer. And it's really not an intuitive answer. If you stop and think about it, that why does a squared plus b squared equals c squared, where c is the length of the hypotenuse and a and b are the lengths of the sides of a right triangle, that probably just doesn't necessarily intuitively make sense, but we'll have all memorized that. But there's a lot of creativity in how we can prove it. But like I say, no one has come up with a story that disproved it.
Yeah, and I do think you're right. As I was thinking about that, I was thinking, because it's baseball playoff time, and just thinking about a square, diamond, whatever you want to call it, and how, why would that just be intuitive that, the distance from home to second is the square of the distances from home to first and first to second. And I'm like, and adding those together, it's like, no, that's not really intuitive,
No, it isn't. However, interesting enough that it is not true if we, perhaps even in your example, it is slightly off if we're talking about the real world, because in the real world, the distance from home to second, even if we say the field is flat, the field is still on planet Earth, and planet Earth does not obey the assumptions of Euclid, and specifically the parallel postulate. And so the fifth postulate of Euclid talked about parallel lines, and that postulate works if you have a flat plane. And the interesting thing that a lot of people don't know is that if you change that parallel postulate to the one that's consistent with either a elliptical surface or hyperbolic surface, then the Pythagorean theorem does not hold. And so if we took the slight curvature of the Earth into play, then none of those theorems hold true. And so, it's really interesting how math is so concrete when we keep the assumptions fixed, which are, like in this example, the 5 postulates of Euclid. Keep those 5 assumptions fixed, and we are locked into the Pythagorean theorem. But if we change the 5th one, which we do when we are talking about something that's not a flat surface, a flat plane, then that formula no longer applies. And so that's where math, again, kind of surprises us when we think, well, this has to be true, but it is still based on the assumptions we made before we tried to prove it.
Well, and the rule-based idea, the idea of having a set of rules, like you said, the Pythagorean rules or any type of rules that you use in math to be able to get to the right answer, is kind of what we're pushing against a little bit. Not that that's wrong, but it's just too mundane. The idea that if you're a mathematician, you memorize a bunch of rules and then you apply those rules, Right. Saying it that way just sounds brutally boring.
It is.
But that's kind of what you're trying to change.
Right. So, like, for example, here's a really boring question of what is, let's say, 102 times 98? If I was going to give you that question, how would you go about solving it?
Well, since 100 times something is easy, so you take I guess I'd split it into 100 times 98 and then add 2 times 98 because that I could almost figure out in my head,
Oh, yeah, that's impressive. I actually, if most people I think would say I'd just get my calculator out and punch it in. But you kind of sitting back and think about it, you notice that 102 is very close to 100. So you can do 100 times 98 in your head. And then you can do 2 times 98 in your head and then add those two together. And so that's a really creative way of solving it that uses imagination in order to get to that answer. And of course, you arrive at the same answer that you do if you plug that into a calculator. Another way of looking at it is that 102 is 2 above 100 and 98 is 2 below 100. And so we could think about this kind of like an expression of 100 plus 2 times 100 minus 2. And if you remember in the FOIL method, way back in algebra of like a plus b times a minus b, the result of that is a squared plus ab minus ab and then minus b squared, where the plus ab and minus ab cancel. And so what you're left with is a squared minus b squared. And for this particular case, a squared is 100 squared, which you're already going down that path, which is 10,000. And then b squared is 2 squared, which is 4. And so we can also arrive at the correct answer by saying it's 10,000 minus 4, which is 9,996. And so that solution is just another imaginative way to arrive at the same answer. And so in one sense, the answer is fixed, but even in a very simple seemingly boring question, there's a lot of room for imagination.
Yeah, and I think that's the imagination coming back to that again. Kind of the goal of one of the goals of Intersecting Us is from the math side of things is to try to look at things from a perspective that has more meaning, has more joy. We've been using lots of words like that versus a simple rule learning where you just you memorize the rules and then apply them. And you've already given some examples. One example, the Pythagorean theory on a non-flat plane, that the rules don't work. So then you got to come up with new rules. But you're going even farther by saying it's not just the only thing you're doing is not just following rules, but you could actually do it in a different way, in an imaginative way.
And really what this boils down to is that it changes our perspective of math being something that's fixed. There's only one right answer, to something that there's plenty of room for growth. There's plenty of room for new ideas, new solutions. And that when you think about math in terms of a growth subject rather than a fixed subject, it changes your whole mindset as to how you think about math to begin with.
Well, if you change your perspective, then if you're in a field that has math as its discipline, if you're in a vocation, a job that has that, this can actually have some benefit to your life, not just doing math stuff. It can have the way you even look at the meaning of your life and the purpose of your life and the joy and the beauty in your life. Given you're going through these disciplines, it can make you getting your mind to start thinking about things in an imaginative way can, I guess my point is, can cross over into other things, not just your discipline of whether it's actual science or applied math, whatever you're doing. It can have more benefit than just that.
Mm-hmm. I actually had kind of a wild idea this morning on my way to driving to work that I wasn't thinking about the podcast, but it actually kind of applies here. So I'll share it with you, and you can tell me whether you think it's a good idea or not. But it does tie back into this fifth postulate of Euclid, the parallel postulate. And so, Euclid came up with this literally a couple thousand years ago. And ever since the beginning, mathematicians have tried to prove that postulate rather than assume it, because they kind of did not like how the postulate was worded. It was very long. It was very awkward, and it did not fit with the other four postulates that were very short, very clear, and just had a different tone to it than this parallel postulate, which stood out like a sore thumb. And so mathematicians thought that, well, let's see if we can prove that postulate, and then we don't have to assume it, and we can, boil it down to four nice, short, and clean assumptions, and, Euclidean geometry will be that much cleaner. And so they've been trying to figure that out for a couple thousand years and never been able to accomplish that until the 1800s, when they actually were able to prove that it is impossible to prove the fifth postulate based upon the other four, and that there is no way to do that. And so if you think about this, what math people have been doing is they've been wrestling with a problem for 2,000 years. And so I don't know how many problems we as a culture are willing to wrestle with for 2,000 years. We are in a culture now where we want to know the answer, and we want to know it today. And yet math is a discipline that has allowed us a structure and a framework where we can't just come up with an answer that we want. It needs to meet certain logical requirements. And so those boundaries are in place, and it's a discipline. And even though the greatest minds have been looking at that for a couple thousand years, no solution arrived. And so math people all agreed that this is still an unsolved problem. And I just think about that in terms of other cultural issues that we have, where we don't like to wait for an answer. We want to know, is coffee good for us or not? Is caffeine good for us or not? And we have all these things we want to know, and we expect to know the answer today. And we aren't really patient in waiting for it. In the other sciences, we don't usually have an exact right or wrong answer like we do in math. And so math has that benefit where we know that we haven't arrived yet. Whereas in other, questions and problems, that is not quite as clear, where some people say, hey, we know the answer now, or others may say, well, maybe we don't. And, you get that debate about whether we've got the right answer or not. So I just kind of thought that was interesting, how different math is in that compared to many other topics that are talked about in our culture.
Well, as you were saying that, that came to mind was a little it's not really philosophical, but just the idea of knowledge. We have probably more knowledge now than we've ever had. I mean, that makes some sense because of time. You're probably not going to go backwards, although you could culturally, I guess. But knowledge, having the information about what is correct or what seems correct is good. But wisdom is a little different thing there. It's taking the knowledge and applying it to useful ways, whether it's, like you said, beauty, it makes me feel good, joy, or just utilitarian use, whatever. But I think the wisdom is we haven't really talked about that, but that just came to mind. Knowledge and wisdom are not necessarily the same. Knowledge would be learning all the formulas and being able to apply them. And that's great. Not everybody can do that. And if you can do that, great. But wisdom would be, why am I using this? And when should I use them? And when should I step back and say, I need to know more than just this knowledge to be able to even do this?
Yeah, I had never thought about it too, but I think that's something we can continue to press in on, because I think that there's a lot in there. I think you and I both, and outside of math, we talk about the difference between knowledge and wisdom, and we see that as it applies to life. But I think what you're saying is that also applies to math as well.
Yeah, and I think even when we talk about math and how you look at it as part of life and the perspective of trying to live a life that's worth living, as they say, and all those types of things. But when you get into problems, as an interesting, we call them a math problem. Well, what about a life problem? You get a life problem where you've got to make a decision, whatever it may be. Knowledge is wonderful, but wisdom is going to have to be in there. You can't be wise without the knowledge. I realize that, but how should at what level that comes in? So it's interesting as we continue into going into this math stuff and getting into ideas of imagination and all that. It's like, I never really thought about it till now, but maybe the imagination and being able to use that well in your mind is what helps wisdom work better. Maybe that's part of that quotient. We should write a book or something. This is good. Someone should be writing this stuff down. It's really
well. How about if I, rather than write something down myself, how about if I read something that is a quote I recently read from a book that I've talked about before. It's called "Mathematics for Human Flourishing" is the book, and it's written by Francis Su. That really connects to what we're talking about. And here's the quote. It says, "If you go through life with the eyes of exploration, every new landscape is an opportunity to imagine fanciful things, exercise your creative skills, and discover hidden treasure." And so that was the quote. And I thought he put that, he worded that extremely well, much better than I think I could have worded it. But I felt like it was a good summary of what I'm trying to communicate today.
Yeah, and I think that it does. It summarizes our podcast today, and really intersecting us as an entity, that you're trying to use exploration, imagination, and trying to find, like you said, the hidden treasures that are there, which will give you joy and beauty and all those things. So yeah, that Mathematics for Human Flourishing is a really good book. So
right. One thing I just happened to notice, I hadn't noticed before, is that word exercise your creative skills. And, we often think that, well, some people have math skills and others don't. And that generally is not true, that, some people are born with it and some people are not. like a lot of things, how good you are depends a lot on how much you exercise, whatever skill you're talking about. And so if you're one of those people that don't think you're good with math or you don't think you have creative skills, we're going to continually challenge that notion because we think otherwise. We think you do have those skills, but perhaps what's missing is an opportunity to really exercise those skills.
Yeah, and look at it from a different perspective. You may have just been trying it from a starting point that doesn't work for you, and maybe a different starting point would be more helpful. Well, good. This is, as we sum up here, it really does that quote that you just read, and the idea of imagination in math is kind of a summary or a way of looking at what we want to do at Intersecting Us, and kind of try to get people to look things at different perspectives that doesn't just go through, just obviously math or even philosophy, but life. And that's what we're really about here. So this has been our podcast for today. I hope you enjoyed it. Join us next week for another one. We'll be getting into more about how to make imagination and life and math all come together as we exercise our life and try to be persons that look at things from different perspectives and find joy and happiness in it.
This has been the Intersecting Us podcast. To further engage with Intersecting Us, go to intersectingus.com.